A star is a war between two forces. Gravity, the most patient force in the universe, constantly tries to crush the star inward, pulling every atom toward the center. Pushing back against gravity is the energy released by nuclear fusion in the star's core, where hydrogen atoms are smashed together at temperatures of 15 million degrees to form helium, releasing torrents of light and heat in the process. For billions of years, these two forces hold each other in perfect balance. The star shines steadily, a sphere of fire suspended in the void. But this balance cannot last forever, because eventually the star runs out of fuel. A star like our Sun will die gently. When it exhausts its hydrogen, it will swell into a red giant, engulfing Mercury, Venus, and possibly Earth, before shedding its outer layers into a glowing cloud called a planetary nebula and leaving behind a dense, cooling ember called a white dwarf, roughly the size of Earth but containing the mass of the Sun. A white dwarf is held up not by fusion, but by a quantum mechanical effect called electron degeneracy pressure, the resistance of electrons to being squeezed into the same space. It will glow faintly for trillions of years before fading into darkness. But stars much more massive than the Sun, those with 8 or more times its mass, die in violence beyond imagination. These giant stars burn through their fuel at a furious pace, fusing heavier and heavier elements in their cores, from hydrogen to helium, helium to carbon, carbon to oxygen, and onward through neon, silicon, and finally iron. Each new fuel burns faster than the last. A massive star might burn hydrogen for 10 million years, but burn silicon for just one day. And iron is the end of the road, because fusing iron does not release energy. It absorbs it. The moment the core fills with iron, the star has built its own death sentence. With no fusion energy to push back against gravity, the iron core collapses in on itself at a quarter of the speed of light. In less than a second, a core the size of the Earth is crushed into a ball just 20 kilometers across. The density becomes so extreme that protons and electrons are forced together to form neutrons, and the collapsing matter slams into this neutron core and bounces outward in a shockwave of unimaginable power. This is a supernova, the most energetic event in the universe after the Big Bang itself. For a few weeks, a single exploding star outshines its entire galaxy of 100 billion stars. If the original star was massive enough, between about 20 and 40 times the mass of the Sun, the neutron core left behind after the supernova cannot support itself either. Neutron degeneracy pressure, the force that holds neutron stars up, has a limit, and gravity overwhelms it. The core continues to collapse, crushing matter beyond any known state of physics. It falls inward past a boundary called the event horizon, the point of no return where the escape velocity exceeds the speed of light. Nothing, not matter, not radiation, not even light itself, can climb back out. A black hole has been born. The black hole itself is invisible, a region of space where gravity has become so intense that it has punched a hole in the fabric of spacetime. But its presence is unmistakable. Gas and dust spiraling into a black hole form a superheated disk of material called an accretion disk, glowing white-hot with temperatures reaching billions of degrees as friction converts gravitational energy into radiation. Jets of matter and energy can shoot from the poles of the black hole at nearly the speed of light, extending for thousands of light years across space. In 2019, the Event Horizon Telescope captured the first direct image of a black hole, a glowing ring of fire surrounding a dark shadow at the center of the galaxy M87, 55 million light-years away. Black holes are not cosmic vacuum cleaners, sucking in everything nearby. At a distance, they exert no more gravitational pull than the star they formed from. If the Sun were magically replaced with a black hole of the same mass, Earth would continue orbiting exactly as before, just in darkness. But at the centers of most galaxies, including our own Milky Way, lurk supermassive black holes millions or billions of times the mass of the Sun. Monsters that grew by swallowing stars, gas, and even other black holes over billions of years. How these giants formed remains one of the deepest mysteries in astrophysics, a question that ties together the birth and death of stars, the evolution of galaxies, and the ultimate fate of the universe itself.